Thanks.
Okay, fantastic. So I want to kind of not clarify, but add a reference. Yesterday, I forgot to say that this non-trivial topology bound, which is basically the bound from below of the superfluid weight that was done in BDG by the first row of people starting with a Finnish group, was actually shown to be not only a BDG property by Monte Carlo, by Perry et al., to be basically in a fully interacting non-mean field model. Okay, so I want to say that, and then we stopped kind of here, where I showed you that there's a mapping between the eigenvalues on the L lattice, those on the or the orbitals on the L lattice, the orbitals on the L tilde lattice. In order to have flat bands, you need the orbitals on the L lattice to be larger, number of them to be larger than the orbitals on the L tilde lattice. And there's a one-to-one mapping between just the orbital content of the L and L tilde lattices and the flat band eigenvalues at the high symmetry points, which in turn, for certain symmetry groups, give the topology character. So if the topology character is given by the eigenvalues, you're going to know it. And I remind you that this equivalence tells you that the symmetries, that the symmetry eigenvalues of the flat bands at high symmetry points, which is this B vector, the B vector will tell you that you have a, whatever representation you have here, here, and here, is basically just given by the difference between the representation of high symmetry points of the orbitals on the L lattice, which you know because you know these are just the atomic limits of these orbitals, the elementary band representation, and those on the L tilde lattice, which you also know. Okay, and because of this minus sign, then you have basically a kind of a natural way of understanding why flat bands in general, or exact flat bands, are likely to be topological, at least for, if you don't have a large number of orbitals. Okay, so now there was a question yesterday which I delegated to this side of to today's talk, whether you can get degeneracy points between flat bands and some dispersive bands by this strategy, and the answer is of course yes. Now, in the past, there were some theorems that, for example, there's a famous theorem, I'm not sure if by Milke, I think it's by Milke, that the line graph of a bipartite lattice has degeneracy points between the flat band and the dispersive band. Now, the line graph, as we know now, after this talk, is basically just, the line graph is basically just, an integration of one of the lattice in this S orbital construction. If I take this, in this S matrix construction, if I take this S matrix construction with this Hamiltonian, integrate one of the lattices, I obtain the line graph lattice. And there's, as I said, this theorem by Milke basically says that the line graph of bipartite lattice has to have, well, first of all, has to have a flat band because it does, and we can understand it from the S matrix, but also has to have degeneracy points with the dispersive bands. But in fact, not on this, this is a sufficient requirement that you have a line graph of a bipartite lattice, but it's not necessary. So this formalism, we claim, encompasses cases that are not picked up by the bipartite theorem, which is restricted in the sense that it's valid for line graphs so for a subset of these lattices. Okay, so let's see how you can get the dispersive mode, the dispersive to flat band degeneracy points. So first, let's look to the left. There's no dispersive to flat band degeneracy, but basically you can see, the appearance of a flat band in a non-chiral symmetric, energy symmetric system, etc. And this is a line graph. This is sorry, not a line graph, but an S matrix construction of S orbitals on the L lattice, which shop, mid bond here between S orbitals, for example, on the L tilde lattice, which are the red ones here, which are at the corners of the triangles. Okay, and of course you have two atoms here. You have one atom here. You're going to get one flat band. Okay, this is the one flat band that you're going to get. And how do we find out its representations of asymmetry points? Well, these are S orbitals, okay, at what's called the 3F Wyckoff position, okay? And these are the S orbitals at the 1A Wyckoff position, okay? So these are these ones, okay? And then you can just leave it, okay, like these three, for example. And then you go to the Bilbao crystallographic server and you find out this, the representation is called AG. This is the EBR of these. This is the EBR of the elementary band representation of the atomic limit elementary band representation is, Zach talk for atomic limits. You can have them tabulated now with the crystallographic server, and you take this difference and you find these eigenvalues. Okay, and then any model you're going to build that has this S matrix construction, you can put in next nearest neighbor hoppings. You can put in any types of hoppings you want. Okay, you're going to get this flat band, and it's going to have the same eigenvalues. The dispersion is going to be a bit different, but it's going to have the same eigenvalues. Okay, now to the right, we now have a model where I have, 3 S orbitals, one at each of the threefold Wyckoff positions. These are basically the Kagome positions. Okay, here the black dots. Okay, these guys, and the L tilde lattice is an S orbital at the hexagonal, at the graphene position. Okay. So now you're going to have how many flat bands? Where you're going to have 3 minus 2, 1 flat band. Whereas here you had 2 of them. Okay, they were degenerate. Here you have 1 flat band. Okay, and you want to find out its eigenvalues at the high symmetry points. And what you do is, again, you do this subtraction. And this subtraction, you go on the Bilbao crystallographic server, you find this guy again, and you find this CBR of the S orbital at the C2 symmetric Wyckoff position. So the 3F, the black dots, minus the EBR of the S orbital at the C3 symmetric position, which is the hexagonal position here, and you take their difference. I just need to delete to refresh the screen. Okay, and then what you find, if you take this difference, what you find is that, you know, this difference in momentum space, this has some representation in momentum space. They're tabulated at the elementary band representation function of the Bilbao crystallographic server. This is another, sorry, this is another representation of momentum space. You can take their difference and you find out that at the K point, you have a K1 representation. At the M point, you have an M3 minus representation. You know, this is the one-dimensional representation. You know, it's got to be the C3 eigenvalue 1 representation. Okay, and this is M3 minus representation, C2 eigenvalue minus. Okay, but then you find that at the gamma point, you can't take the difference. Okay, in other words, at the gamma point, if I did the flat band, if I did the flat band vector by this formula that I gave you before, I find a contradiction at the gamma point. I find that, you know, the gamma point representations would be gamma 5 plus minus gamma 4 minus. These are two different representations of the symmetry of the local, you know, point group at momentum at the gamma point, is the point group of the lattice also. Okay, so these are two different representations, and I find out that if I take this minus, I obtain this. Okay, gamma 5 plus minus gamma 4 minus. But there's no meaning in a minus in terms of representations. Okay, so this means that there's no way here to completely separate the flat band from another band. Okay, so this actually means that here I have not a flat, at the gamma point, not a flat band separated, okay, but a flat band that is connected to another band that provides this gamma 4 representation, so that you don't have to take a minus, which doesn't mean anything. Okay, so this representation at the gamma point is actually gamma 5 plus. Okay, it's a two-dimensional representation. It's gamma 5 plus, and you can write the flat band as gamma 5 plus, okay, K1 representations, M3 minus, okay. And in this case, this is one-dimensional, this is one-dimensional, this is two-dimensional. So you know that the flat band has a degeneracy point with a dispersive band, okay. And that's the way you get all the degeneracy points that you want on the lattice. So by starting with L and L tilde, I also not only can establish the topology if the bands can be separated. So if I don't have the situation with minus sign at a particular point in the K-space, I can find the topology. If the bands, if such a situation arises where by taking this atomic limit difference between the L and L tilde lattice, if the situation arises that I have a difference of representations like gamma 5 plus minus gamma 4 minus, then it means that I cannot, you know, well, that would be nonsensical to say that this is a one-dimensional representation, because it's a difference. And states have to come in sums of representations at high symmetry points in the Briand zone. And that means that I have a degeneracy point. Okay, so I hope that's clear. If it's not clear, please ask questions. So now you have a one-to-one mapping between, not a one, again, I keep saying one-to-one. It's not a one-to-one mapping, it's an orbital. Once you know the orbitals on the N and L tilde lattice, you can get the topology or the degeneracy points of the flat band. But there are, you know, many L and L tilde, different L and L tilde lattices that can give you the same flat band and the same degeneracy points. Okay, so now I want to basically point out that this you know, graphene model, for example, twisted bilayer model, that was 10-band model that was done by Poe et al. By breaking particle hole symmetry. Actually, you can understand it also by a flat band by an S matrix construction. And, you know, the L and L tilde lattices are basically just given by these lattices. Okay, these are the L, these are the L tilde lattices.
Question?
Yes. Oh,
yeah.
sorry.
Mikel Garcia, what is the robustness of the flat band against longer range hoppings?
There is 100% robustness as long as you have your Hamiltonian is this. Okay, or your Hamiltonian is this. Notice I didn't tell you what S of K is. Okay, it can be any hoppings, any orbitals. It's 100% robust. You can have any hoppings, any orbitals. It's going to be an exact flat band. So it's a very good question. So, you know, normally if I wanted to start from a Kagome, okay, so if I Kagome with nearest neighbor couplings has a flat band. If I add arbitrarily on the Kagome next nearest neighbor couplings, I mess up the flat band, okay? Because you haven't added it properly. The proper way to add it in the Kagome lattice is to start, if you want to add the next nearest neighbor hoppings, is you start with the hexagonal lattice, okay? The hexagonal lattice and the Kagome sites, okay? These are the Kagome sites. It's a 5-band model. This would be 3, this would be 2, okay? Then you integrate out the hexagonal lattice, and then you can add any type of any long range hopping as you want. So you can recover the flat band of the Kagome for some, you know, ratios of longer range hoppings. But if you just add it directly in the Kagome, you want the next longer range hoppings will spoil the flat band. But that's the wrong way to add it, is what I claim. The right way to add it is to build this 5-band model and then integrate out the L tilde lattice, and then you get the Kagome model, which can have longer range hoppings if you want to, but they will come out of this integration, so they'll have some properties of themselves, such as the tails or whatever you'll get. But this construction by itself, which is, I claim we claim the way to go about building flat bands, doesn't care about how many hoppings, the range of the hoppings. It's a very good question. Thank you. Okay. Thanks. Okay, very good. So for example, this PO model, a 10-band model of twisted bilayer, again, as I said, can be expressed as an S matrix with the L lattice being this, the L tilde lattice being this. Okay, and then there's some theory, which I'll go, you know, I'm basically just going to quote the results. It's not, you know, particularly illuminating, but you can kind of have a set of generators for the flat bands, for gap flat bands and gapped and gapless flat bands. So there's an infinite number of them, but there's a set of generators. Okay, so so then, you know, once you have this theory, well, what are you going to do with it? And the immediate, you know, thing to do with it is, since you know, our collaborators such as Bradley Cano, Korover, Wang, et al., or in more recent papers, Ranieri, Wang, Regnault, and Regnault build this extensive database of materials. So, you know, this now it contains about 70 to 80,000 materials, and you know their topology, and you know, moreover, topology of each set of separate bands that you can take. Now, you know, this might not be particularly illuminating for a system that has a lot of spaghetti of bands here, but for systems, you know, for systems of, you know, 10,000 of them out of the 70,000, which have bands that are not spaghetti, this is, it could be very useful. But you can take all these 70K materials and try to find flat bands in these materials. And, you know, this is again the reason why I wanted to underline these people who've worked tremendously hard on getting these results out. Okay, so there's two things you can do. So one thing you can do is you can find flat bands by brute force. And the way you find flat bands by brute force is just putting a flat band filter on this database, which basically means that what you're doing is, you know, you're putting some criteria. So you have a database and you add some criteria to it. And these are the criteria that we've added. You know, if you have a length, you basically ask for the bands to be flatter on a length L, which is at least, you know, one high symmetry line in the Briand zone. You know, you can give them a score, how high, you know, how many what's the flat band score, how many, basically roughly how many lines around the Briand zone they're flat on. And then you can ask, you know, several things, such as ask to get the bands that are flat within and end within 1 electron volt of the Fermi level. You can change this to half an electron volt, etc. And you can ask for the flatness of the bands to be, you know, roughly, in our case, we put 50 electron volts. Now, you know, this is kind of an arbitrary number since we don't have an estimate of the interactions in these bands. But, you know, you can pick your value. And in fact, in the website that we've built for this, you can actually change these numbers and, you know, find different things. Just be patient with the website because it's loading things live, so it's actually not very fast. So you might think it's not working, but it is working. It's just you just have to have kind of a Spartan attitude and play with it for a while, and it'll work. It's just not very fast because it's loading a lot of information, such as density of states also. And this is another way to just brute force get these systems. For example, you know, you look for peaks that are larger than, you know, the average or smaller width than the average, etc., at the Fermi level. Okay, so you do this and you do this brute force, and you find the following number of materials that you can then go to them one by one by hand, and so that obviously takes some time, and curate them. So there's you know, flat atomic bands, nice flat atomic bands. There's at Fermi level. So I remind you, this is out of 70K materials, 30K number of materials. Non-atomic flat bands, there's this number. And then you can, you know, go through all of them by eye and try to, you know, still use the best machine learning that we have, which is the brain, I guess, and come up with a curated list of materials, which is not that large a number. Okay, so that's one way. That's the brute force way. The other way.
Before we go to the other way, there's a question. Yeah. Question on the effect of hopping from sites of the same sublattice. If we did not ignore them completely, what could be their effect?
That's a very good question again. Notice here that there's in the L tilde sublattice, they don't matter. Okay, so B of K is hoppings between the L tilde and L tilde, so they don't matter. As long as these conditions are satisfied, Okay, so for example, here, in this case, where A is a complete constant, so this condition is now, this is one of the Hamiltonians that satisfy the conditions I put on the previous page that Kalugar and Chu found. But basically, this, you can see this A is constant. So if I have this, there's no restriction on SFK and BFK. Okay. So that's, I think that answers the question. Very good question. So you can have, now if I had coupling within here, within, you know, any Hamiltonian can be expressed like this. Okay. Any Hamiltonian can be expressed like this if I don't have any restrictions. So obviously not every Hamiltonian has flat bands. Flat bands are very specific. So these conditions are important, which are basically conditions on this AFK. Okay, so if I start messing here in this simpler case with AFK, I'll deflatten the bands, and their bandwidth will basically be proportional to how much I mess up the flatness of the AFK. So basically, I cannot have a lot of hopping in the L sublattice, but I can have a lot of hopping in the L tilde sublattice. In fact, any type of hopping.
There's a follow-up question. What is the meaning of best flat bands?
Yeah, that's also a good question. And, you know, it's also, you know, the answer to this I would give is the answer to what's the meaning of the word best. That's also in the eye of the beholder, you know. So for example, I would say this band is pretty good. Okay, but it's not the best. It's pretty good because it's got, you know, you have a flat band over everything, but it's not the best because, you know, it doesn't stay flat here. You have a lot of crap coming here. It's like, basically, it's good. It's good, but it's not the best. Now, things like this, okay, like this one, which, you know, basically, I mean, well, not basically, clearly independently found by Tsiolkovsky, and because he's also done the experiment while we were writing this paper. This one is also very good. It's actually probably better than the one before because it's flatter on a longer part of the Briand zone. Okay, this guy. So you can think there's basically anti-crossing here. This is longer on a larger part of the Briand zone. There's still kind of some spaghetti of bands here, but it's a little bit better than the one before. Now, you know, these ones are, you know, also good. This one, there's a lot more spaghetti. This one in manganese 6. Let's see this. Which one is? Let me just give you some other examples. Okay, but these ones, okay, but these ones which are curated, these are really good. Okay, I'm not sure if really good means physically anybody interesting, but it certainly means that they're very good in the sense that they're flat over a large region of the Briand zone, like look at this one here. Okay, and there's not a spaghetti of bands around them. Okay, so that I would say is really good. This is really good. So these are ones. So, you know, that's what I mean, that basically we did some curation by hand. You know, this one is really good. You can see it here, as I'll show you. I'll get back to these later. But I think maybe it's important to have this discussion, even if it breaks the flow of the talk. This one is really good. You'd have nothing around it. So, you know, that's why you still need like the human eye to go through them. So that's what, okay.
Yeah,
I can read the.
okay. Yeah, go ahead. Yeah, please.
It's okay. Some from Mikkel, which is the most way of containing friends with particular. Oh, okay. So that's so. There's no efficient way for the public to do that now. So it's not on the website, okay? Just because it's not easy. I mean, you know, you can have a lot of bands. Somewhere on the website tells you, you know, you have a flat band around amongst those bands, but following that flat band, especially if there's anti-crossings, it's not that easy. So there's no particular way for you to do that now. We can probably do it internally, but it's not implemented at the moment, and it's not easy. So the way one would do it is, of course, to go through. You can do it. It just would not be efficient. So you can go through these 345 unique materials. Okay. For example, if you have for these best flat bands, if you want. Okay. Each of them has the flat band. Then you can go on the topologicalquantumchemistry.com website and find that flat band. Also on that website are given the representations of all the bands from the core shells to the highest bands, that the highest orbitals that we took, I guess it's 10, as Maya would know better, plus or minus 10, plus or minus 20 bands. It's below and above the Fermi level or something like this. Okay. But so you can go and do this. Then you can count, you can see which one the flat band is. You can count from up and do it. So you can send, if you have one material that you're really interested in, that can be done. To do this for 345 by hand is not easy. But the information is there to search for, to find the representation of a particular material. If you want to do it the other way, to call all the materials that have the specific representations, that's not done, and we don't plan to do it, even internally. Okay, the next question. Is there a one-to-one relation where all the elementary flat band can be written with those conditions in AFK, only works in one direction? So that's a very good question. So in fact, what you're asking is this method complete? So the question is there a one-to-one relation where all the systems with flat bands can be written with those conditions in AFK, those conditions meaning the degeneracy of AFK, or it only works in one direction? So it certainly works in one direction. If AFK has those conditions, will you have flat bands but not otherwise, right? So you're asking if basically the list is complete. Okay, so the answer that I can give you is that the list should be complete without particle hole symmetry. You can obviously have, so if I have particle hole symmetry, there's another way of building flat bands, which is particle hole symmetry, which changes k to minus k. Okay, k goes to minus k, but then you add inversion. So if I have inversion times particle hole symmetry, then this changes k to k and would take energy to minus energy. So if I have an odd number of bands, I have to have a flat band. Okay, but particle hole is not a crystallographic symmetry. It won't appear in most materials. Okay, you can do some theory where you can have flat Bogoliubov bands with this, and but it won't be of interest experimentally, I think. So inversion times particle hole can get you flat bands. And Kaluger and Chu basically also looked at it, but didn't publish this. But basically, it's not relevant for materials in quantum chemistry because particle hole doesn't appear in most situations in the real material. And whereas this bipartite type of lattice that we have, that you have, appears because, for example, if I have Lieb's model, this condition would only tell you that you don't get coupling between these, okay? This AFK condition, and the only hopping is between the dot and the X. But, that's a physical condition because the distance between these two is square root of 2, okay? The distance between these two, okay? So hopping is going exponentially with the square of the distance. This is e to the minus 2, at least, the hopping between these orbitals, not looking at any symmetry, is at least e to the minus 2 times the hopping of these orbitals. That's a physical condition, okay, that can appear in physical materials. Whereas, so I claim that it's a one-to-one relation if you don't include particle hole. You can write everything like that. Okay. the next question is, when looking at the real materials, is it unique the identification of N, L, and L tilde sublattices? So I'll get to this right now. There are some situations where it's unique. There are some situations where it's approximate. It's also a very good question. So, so I'll get to this now. Very good. Okay, thanks. Okay. Okay. So I spoke about the brute force way, but of course, as Inigo was asking, anticipating basically, the next slide, what we actually want to do is to use also, to complement the brute force way with the non-brute force way, with this line graph, with the not line graph but bipartite SFK method. And basically, we started looking for all the lattices that can have a bipartite structure, and a bipartite structure of the relevant orbital. So if you have an atom, for example, which is not in a bipartite structure, we wanted to have the relevant orbitals at a far different energy than the free energy or than the energy of the active orbitals. Okay. Okay. So you can devise a method that looks for this. Okay. And that method has, you can look at it in two ways. You can find a supergroup method, which is what was asked before, which is based on symmetry, on basically symmetry of graphs. And you can see if a set of coordinates, okay, belongs to a lattice that forms, for example, a bipartite lattice or a line graph lattice, that you can see an exact one. You can see by symmetry. So for example, some symmetry groups like C6V in some planes, right? C6V, which would be a plane in 3 dimensions, would be a plane symmetry group. You know that it supports Kagome lattices if the atoms are in some Wyckoff position. Okay, so you can do a search based on that. You can ask in all the symmetry groups on any planes. So you can do first a 2D search on any planes. Do I get a lattice that's bipartite, or that's Kagome, or that's a line graph, or that's a split graph, which are all included in that in this S matrix formalism. So you can do that. Then you can ask, do I have any pure 3D 3D lattices? And clearly, by just looking at Wyckoff positions, okay, you can see whether you have bipartite lattices with larger number of electrons. So basically, in the square lattice, the simplest way is to realize, if I didn't know anything, of course, in the square lattice, it's very easy to do it by eye. But if I didn't want to do it by eye, I would just ask, are there 2 Wyckoff positions where one of them is connected from the other, and the distance between one and the other, are there 2 Wyckoff positions, one of them with a higher multiplicity than the other? The answer is yes. I have a 2 multiplicity and a 1 multiplicity here. And then I would say, well, and the distance between the 2 Wyckoff positions that have the higher multiplicity is larger than the distance between the Wyckoff position of the higher multiplicity and one lower multiplicity. And then I do another check. Okay, so you can automate this process. So then this will give you this lattice. So you can automate this process basically. There's another question. What will be the effect of the flat bands on the Carroll anomaly in the case of the Wahl symmetry will manifest itself in the transfer measurements? So that's a question that's far off what I'm talking about right now. So I'm not going to answer it right now. Okay, you can keep it live, and if we have time at the end, I'll answer it at the end. But I want to keep concentrating on what I'm going to talk about it now, or the subject of this talk. Okay, this is not an experimental talk, so I'll try to answer it the best as I can at the end of the talk. Thanks. We can keep it live. Okay, so then you can find also a geometric method, which basically tells you, well, say I have some sort of an approximate, some sort of a symmetry, some sort of a lattice where these are not, these things are not mid bond. There's somehow they're a little bit further away, or some symmetry is broken, so you don't have exactly C4, and ask if there's approximate bipartite structure, approximate Kagome. So you can say, I have the Kagome, but I don't have the correct symmetry group. This is the whatever. I don't have the correct symmetry group, so this distance is a little bit higher than this, and a little bit higher than this. Okay, so I have like Kagome triangles which are a little bit distorted. Okay, so you can sort of still find that you can still find that there's going to be a Kagome structure, but it's just approximate. So you can devise obviously geometric methods to look for these type of situations. And what you find is that in all these materials, there's 70,000, I think between 70 and between 70 and 70,000 and 90,000. I'm not remembering exactly. There's also how many materials are duplicates, etc. Okay, there's between these and number of materials, and you find out that there's these types, these number of materials with Kagome lattices on Lie basically means bipartite. Okay, and these many of pyrochlore, and then you find also there's some approximate numbers of symmetries. Okay, there's a lot of them. Okay, and these are some things to try on automated identification. I'm not going to go through it because it's just basically computer just computer searching through the types of lattices that we can get. Okay, but roll these and then kind of cross-check them. Okay, you can cross-check if the materials you found by brute force, kind of cross-check with these materials that you found with the materials you found that have these lattices. And the answer is yes, they do cross-check. There's a high degree of correlation. And you can of course then build a database, which you can find it here, where you can have all these features that you can look for flat bend, and you can even look for the lattice features, which materials have the lattice. So you can play around and find out. Again, it's very slow, so really playing around doesn't work, but playing around with a purpose does work. Okay. Okay, so for example, let's give this example of this material, which is a very clean one with clean flat band. So you can see a huge density of states, large flat band, non-atomic. It cannot be atomic. It's got these huge dispersive that's coming out of it. Okay, etc. And then you have several atoms in it, and then the website basically tells you, well, it tells you the if it's known to be magnetic and it's not known to be magnetic, if it's known to be superconducting and it's not known or unknown. So basically there's no information. Unknown means no information. And again, this information comes from a Japanese database of superconducting materials. The magnetic properties come from the material project. Okay, and then you get a lot of information like the band structure, the topological character. If you go here on the topological database, and then this belongs to the flat band list. And then you get basically also information about what happens when, which atoms form sublattices. For example, these atoms, okay, on some Miller indices planes form a Kagome sublattice. These atoms on Miller indices planes form a Kagome sublattice. Okay. Okay, and then you can find out that this has also bipartite sublattices, not just Kagome. Okay, etc. And you can find all this information here on this website. Okay, so these are several of the materials that are that we showcased. Now, basically, what you can also do, and we did for these materials, you can do so they all have these type of S matrix constructions, but what you can do is you can do a ab initio Vannierization of the Hamiltonian of these materials, and you can find the Hamiltonian without any input, just by brute force. And then remarkably, what you find is that a Hamiltonian basically is of this form out of the Vannier states, and then some A here, and then some B of K. Okay, and this is just kind of a brute force calculation that goes the other way without knowing anything. You basically are proving that there was the question of whether whether this construction is complete, and this is basically a check on the statement that I believe it is complete. All these materials, if you just do brute force ab initio, will spit out a Vannier Hamiltonian, a Vannier type binding Hamiltonian that looks like this. Okay, this is another question. And you got to have flat bands, you need to have constant eigenvalue on the L sublattice. How necessary is to have really flat bands? How necessary is this to have really flat bands? How can you check this on a real material? Well, again, it's necessary to have exact flat bands. Now, to have depends what you mean by really flat. Okay, it's again a semantics question. Any perturbation you're going to have to the constant eigenvalue on the L sublattice will mess up your flat bands. If the perturbation is larger, you mess them up more. If it's not larger, you'll mess them up less. How can you check this on a real material? Well, as I said, the way we check it is, or maybe I didn't say it well enough, but the way we check it is, for example, we look at the bipartite sublattices. I gave you this example, which is the simplest one you can visualize. We look at the bipartite sublattices, for example. That's one way. Then we ask, what's the distance between these atoms and the distance between these atoms, okay? And then we put a cutoff to that distance. And we neglect all the ones where this distance is smaller than a cutoff, because we want, this is the distance that will govern the L sublattice hopping. Okay, so you can do this in an automated way. Of course, there's a lot of background to this that's kind of like not relayed by me now, but this takes a while. You have to look into different cutoffs. You have to make sure you're not missing things. You look back, you test some things, you talk to people that know experimentally some flat bands. You ask them if to give you some, like Joe Chilkelki, to give you some materials. Then you find you see if you've missed those, etc. So there's a lot of back and forth to optimize these cutoffs that you're using. But basically, the strategy is geometric, to look for to see whether this constant eigenvalue on the A sublattice exists. Basically, looking for low hoppings on that lattice. Very good question. Okay. So, right, okay. So for all these materials, as I said, if you do the brute force, get answer this question. There's another question I'll answer it after the next slide. You get a correct S matrix construction. Okay, so for example, these are the ones that I wanted to show you. But there's as I said 345 or 340 of the ones that we've curated. Now the website contains thousands of them because they're also the ones that are not the best. You're going to see in a lot of them some spaghetti of bands. Okay, but the reason why I find these more interesting is, and that might not be the case. It might not be the case that they're the most interesting. It might be the case that the other ones are interesting. Is that they're tagged as non-magnetic. So the materials project tags them as non-magnetic. So normally these guys are not known, even though they have flat bands at the Fermi level. For example, this one has it exactly at the Fermi level. Okay, they're not known to magnetize, and hence maybe some other order. Normally they should magnetize. There's some other order developing. Even for the ones that magnetize, which is here, it would have a ticker M, which would be magnetic. Even for the ones that magnetize, those ones that magnetize, since these bands, we've only looked at bands which are non-atomic, flat bands which are non-atomic. If you look at flat bands that are atomic, there's other lists. By the way, the flat bands that are atomic are also included on the website, but the ones that we showcased, none of them are atomic. So they shouldn't be atomic. So if you polarize them, if you magnetize them, similar things should happen, as Oscar said in Twisted Bilayer. The topology of the underlying band should imprint in the topology of the many body state. Okay, so even the magnetic ones I think are very interesting, and basically we're waiting for experiments. Okay, and I think I'm going to stop here, and I wanted to talk a little bit about interactions in TBG, especially about the charge 2 excitation, and basically to show you how the topology of the flatbeds gets imprinted in the charge 2 excitations. But I've run out of time, so I basically Oscar is going to talk about this, so listen to those talks carefully, because all of this will be covered there. Thank you.
Thanks, Andrei. Well, you did start a bit later, so I don't know how long would that take you.
Yeah, it's probably going to take me a while. I like to actually do anything meaningful is going to take me a while, and I know Oscar is going to talk about the charge 1 excitation, which
we can take questions
a little bit, but yeah. So basically, there's a lot of overlap. So I think it's better to just stop here.
Okay.
Okay. So, what is the effect of SSC in this particular Rani-Hamiltonian? Which particular Rani-Hamiltonian? There's a question. What is the effect of SSC in this particular Rani-Hamiltonian? What was the particular Rani-Hamiltonian? If you could write again. Yeah,
you can type it below the question. Actually, for the first one, maybe I have a suggestion, which is, so Claudia is going to give a talk, and maybe that's a question for Claudia as well. How does flat bands affect the Kerr anomaly? How would you expect it?
Yeah.
I mean, you can take your take if you want.
Yeah, that's a good suggestion, because my answer to that is I don't know. So I know that Zahid Hassan claims that flat bands are very important. Okay, I just listened to one of his talks 4 days ago, where he was basically claiming the flat bands are very, very important. But I don't know more details. So the answer is I don't know, but maybe some other of the panelists knows that also, maybe you know.
I can say something. I mean, I don't know about this particular material. I haven't really looked at how the flat band kind of interplays with the rest of the band structure, but in cobalt silicon and rhodium silicon, also materials that you guys predicted as multifold semi-metals, you have basically charge 2 crossing with 3 bands without spinor coupling, and you have a flat band crossing in the middle. And if you look at the Landau levels, which I think you also calculated, you see that there are basically 2 chiral Landau levels levels, and you still get a chiral anomaly with those, even with a flat band in the middle. You would, in principle, still, no matter where you put the chemical potential, you would count the number of chiral Landau levels that you have, and you would have in that case too, and you would still have a chiral anomaly. But maybe in this material, things are more complicated because it's also magnetic. So.
I see. So that flat band. So yeah. So you're right. So that flat band in the middle does belong to this. You think it's the same flat band as this? That would be very neat. You're saying it's the same flat band, basically, roughly.
Possibly.
Oh, that would be very neat.
I don't know, but I don't know that
was
well.
very flat, I agree. Okay. Yeah, that would be very neat. Okay, very good. Yeah, that's very interesting.
But yeah, but I would suggest to keep that question also for Claudia. I think next Thursday and tomorrow, but following Thursday. Yeah.
Okay, so the answer. So the second question was, what is the effect of SOC in this particular Vanni Hamiltonian? The Hamiltonian was AFK. Okay, so again, SOC is included. This construction includes SOC. Doesn't have anything to do with SOC. No SOC. This thing, AFK, SOK, BFK can have SOC, cannot have SOC. You do whatever you want. Okay. And the Hamiltonian, with SOC, the SFK is going to look a bit different than the SFK without SOC, but this construction does not depend on whether you have SOC or not. Right? So I know that in the literature, all the flat bands that we know, or most of them, are with are without SOC, and they're only with s orbitals, and that there's only scattered examples of flat bands without SOC, but that's a historical kind of reason. The historical reason is that the flat band people are all graph theory people, okay, and they were just doing graphs, but it doesn't matter. You don't need to sacrifice any SOC. This SFK and AFK and BFK can include SOC, and the Vanni Hamiltonian that we obtained from ab initio certainly does include SOC, and it goes in this form. Okay, there's a question: how do you identify which flat bands, from Martin? How do you identify which flat bands are atomic? Good question. Okay, so let me show you how to identify. For example, you look at this. Okay, so number one, the way you identify it is, so you have the website, and its eigenvalues at high symmetry points. Okay, so you first check that the eigenvalues of high symmetry points are compatible, are those of an atomic band. If they're not, it's topological. But you first check that those eigenvalues are those of an atomic band. Okay, you found a flat band, and if they're those of an atomic band, then it's compatible with an atomic limit. And then you look, for example, at the distance of the lattice. If the distance is too large, then again, you've got an atomic limit. Then you look at this gap. This gap is 1 electron volt. Okay, there's no way you can get such a large gap in a topological system, because they're usually spin orbit coupling gaps, and largest ones are 300, 400 electron volts. And there's only a couple of materials, bismuth selenide, with those type of gaps. Okay, so these things you can do without running, of course, in order to fully prove it, you'd have to run a Vanni-Rice calculation, show that the Vanni states are localized on the orbitals, or hybridized away from the orbitals, but they're exponentially localized. But then that would be expensive. If you wanted to do it for 70,000 materials, you couldn't do it. There's no way you can do it even with a supercomputer. But you don't need to do this, right? You can. That would be an overkill. What you can do is, again, just look at these bands, check that their eigenvalues are compatible with those in the atomic limit, and then look at how far they are, how the gap is. Then you can also look, this geometric method that we have. What's going on here? Okay, somehow, because I have annotate. I shouldn't have annotate, sorry. Sorry, 1 second. Let me just clear the annotation. Okay. Okay, very good. So these geometric methods that we have can detect detestable clusters. So for example, if I just have, if we have a cluster of molecules, so if I have a cluster of molecules of atoms, a molecular cluster, okay? If this, and the lattice unit cell is large, but it's around another, okay? Then you're gonna get molecular. So this is large, this is much larger than this, L1 much larger than L2. Okay, so there's geometric ways also of identifying a trivial atomic band. So you first find the flat band, you find its eigenvalues. If they're compatible with an atomic limit, you go further, you check the geometry of it, etc. So you can identify all the atomic limits. Okay, very good. Another question is from Mikkel. Could a procedure like this be take a 2D material, find a Vanier type binding, and use the SMH construction to predict a bilayer flat band as graphing based on lattice and positions of Vanier orbitals? Okay, so that's a good question, and the answer to this is anything is possible, but this would be remarkably hard. Okay, and the reason why it's remarkably hard is basically the reason why you can't predict Moire band structures really for anything else but these simple graphing cases. So, for example, I wouldn't trust any Moire band structure of tungsten ditelluride, okay? A much more complicated system. So once you have a Fermi surface, once you have, Fermi surfaces, okay, if you twist them, then you're going to have a large number of degrees of freedom coupling. It's not like in twisted in bilayer where you couple the Dirac fermion to another Dirac fermion. And especially if you have many Fermi surfaces in the original material, once you twist it, things will couple all over the place, and you won't get something clean. And I wouldn't trust it now. Also, it's not guaranteed that if you start with an exact flat band, once you twist them, you're going to end up with a flat band. And the reason for that is, the hopping between layers is also of order electron volts. Even graphene is 0.3, 0.4, something like that, electron volts. So, or 0.2, something like that. So any possibility that you'd get a bandwidth of that order could happen if you start with flat bands. So I wouldn't say that this is so far a fruitful path, although I would say that it would be very interesting if one could make it work. Of course. Now, at the current state, I think you cannot predict basically accurately the behavior of twisted layers, with the exception of some very simple ones. Certainly for something as complicated as tungsten ditelluride, which is, by the way, not very complicated from a DFT point of view, not incredibly complicated. I mean, it's complicated, but not incredibly. Not a huge amount of bands. I wouldn't trust any more event structure that's predicted. So yeah. So your question is basically a whole research field that could be developed. It's very hard. Okay. Chiara is asking, among the flat bands which are identified as flat atomic from their band representation, could they have non-trivial topology detective adamines? Yes, the answer is yes. And actually, the same. So, okay, so the question, which is again a very, very good question, is basically you have these eigenvalues. We have these eigenvalues of the flat band. Okay. And so far, I've mentioned only that the flat band, okay? So far, I've mentioned only that the flat band has some eigenvalues. What I didn't mention, and what's less looked at, but the fact that it works is in the flat band construction paper, but it's not analyzed to the full extent, is that this works also for systems where you don't have eigenvalues, for example. So let's take a lattice like this, where you have no unitary symmetry, but you have C2T. Okay. Okay, so you have C2T, and here you have these things. Okay. And on this lattice, C2 C2 times time reversal basically still fixes you some Wyckoff positions. Okay. And this is a Wyckoff position. This is 1A, right? It's invariant under C2 and time reversal. This is 2B. This is 1A, actually 1A, I guess this is 1A, 1B, 2C. Anyways, there's some, okay. With C4, I guess also. Well, if I have C4 and C2, let's see, let's not have, okay, so let's not have C, let's not have this. Let's have just, okay, let's have just, so with C2, this is, okay, this is 1A. This is with C2 and T, this is 1B. And this is 1C, okay? Okay, very good. Those are the positions with C2. If I put C4, I have the 2C position, but if I put C values, so I don't want to have eigenvalues. So C2T is an anti-unitary symmetry that doesn't have eigenvalues, okay? Okay, however, you know that basically your flat band will still be given by the band representation here, okay, minus the band representation here, okay, band representation of these two minus this band representation, okay. And actually what you know is that you'll have, we can go through this, but you'll know that you'll have a crossing point and a flat band. And because of C2T, whatever you do to this, you cannot gap the crossing point. Okay, so all this, so even among the band representation that can be identified as atomic limits from their eigenvalues, you can have topology based on non-eigenvalues, such as the C2T ones. So we give an example, and I forgot which one it is, where you have actually exactly the fragile topology of the twisted bilayer graphene coming from a S matrix construction with only C2T. Okay, so it is possible, this formalism of band representations, you know, if you take differences of band representations, is not just eigenvalues. Okay, there's another thing which is the real space indicator, which tells you if you can form a band representation from orbitals at some position or not. And those work also in the case of, you know, anti-unitary symmetry, such as C2T. You won't be able to know if, you know, if you have absolutely no symmetries. If you absolutely have no symmetries, then this won't work. But you could have it, as you said, you could have something identified as a flat atomic band structure from the eigenvalues, but still be topological from Wilson loop. And the C2T case is the perfect example because you have no eigenvalues at high symmetry points. Very good question. Okay. So then there's, how would the number of materials with flat bands, the number of materials with good, that's Mikhail's question, how would the number of materials with flat bands and the number of materials with good flat bands change if more sophisticated treatments of electron interactions like LDA, including the calculations of the database? Well, that's you know, obviously a good thing to try and to do, but you know, I don't know the answer of how it would change, right? It's a research topic. I mean, a lot of them would magnetize. What we've computed is the paramagnetic phase. A lot of them would magnetize. How many of them would magnetize? only God and the person who's going to do the calculation, no?
Oscar has a question.
Andrei, you showed these examples of non-atomic stoichiometric materials with flat bands that were known not to be ferromagnetic.
Or magnetic, or anti-ferromagnetic also.
Oh, I see. Okay. So, for example, the one on top left in this figure, it seems that the flat band is fully occupied. Is that correct?
Yeah. So in this case, so you're right. So in this case, you need to dope it. So Kava's thinking of how to dope it, but they wouldn't. It's not clear that it would stay flat after doping. So yeah. So. But for example, from the topological classification, you can also find when it's an enforced semimetal. So in this case here, it's this guy is telling you, this guy indeed, so this is linear combination of EBRs, which basically LC EBR is linear combination of EBRs, just a name to scratch, but it basically means that it's a sum of atomic limits at the Fermi level. So if I fill all these bands, as you said, it basically tells you that it's a small gap insulator at the Fermi level. If I fill all these bands, so I would need to dope a little bit into these bands. But there are some of them, like this guy is also at the Fermi level. So if you see here in 4 semi-metal, this is at the Fermi level, and this guy at the Fermi level, if you follow it, there's like, well, this guy is a metal, but it's a metal in the sense of like the band dipping in and out. It's actually, in the topological sense, it's an insulator, because it could be right. It could be it's a metal in this sense.
There's a direct gap.
If you follow. Right, exactly, and it's a topological metal. So this tells you that it's a split. And it's just another name, but this is a topological. So out of these ones, this one, you're right, it's a small gap trivial. So you need to dope it, but these ones are at the Fermi level.
I see. Thank you.
Thanks.
Okay, I think there are no more questions. You did a very good job. So yeah, I think we can leave it here. I think everybody's flying out. So
very good.
Thanks for the nice lectures, and yeah, we hope you show up every now and then for the others. And then thank everyone for attending. And I think we can close it here for the day. And please remember to check out the Slack channel. Also, thanks to Jen and Ben Witter because of they're like answering questions live and very with a lot of detail. So I want to thank them here. And yeah, so we'll thank all the speakers and see you tomorrow.
Thank you. Bye.
Yeah, bye.